For this tutorial, I will start by closing the case study model, and I will go to the Exercise 8 folder and open the job name Plane Outlet. We're staying on the topic of pressurized air vessels, however leaving the case study system and swapping over to a simple pumping main. It is 3.2 kilometers long, constructed of 1000 mm diameter mild steel cement line pipe. It is carrying a flow of 715 litres a second, meaning it's moving at about 1 metre per second, and we're looking at a power failure scenario. Your mission is to study a plane outlet connection from the pressurized air vessel and understand how the vessel's air volume affects the maximum head experienced at the pump delivery node, labelled DS valve, and the minimum head experienced at the crest in the pipeline, node third point. I will begin by using the vessel's edit form to check the starting parameters. I can see that the water level is already 46.406 metres and the air volume is 0.5 cubic metres. So I'll run this scenario first, but note these values are disabled. This happens when geometry is defined for a vessel. So let's click the Specify Details button to take a look at how you define a vessel's geometry. The vessel is vertical. There is only one vessel at this location. Its base is 0.5 metre above the node's level, meaning above the obvert level of the main pipeline. It is 2.1 metres tall with a diameter of 0.75 metres. After defining these physical parameters, you would usually not change them from scenario to scenario. What you will change is the initial water level in the vessel, cancelling out of this form. Going into Simulate mode, simulating hydraulics, starting the transient simulator, selecting the only available time step, well, we can't proceed any further with the 0.5 cubic metre case because the air vessel empties early in the simulation. Returning to the editor. Selecting and editing the vessel. Setting the water level to 45.84 metres. Checking that we end up with an air volume of 0.75 cubic metres. Yes, it is. Can you guess what is going to happen this time with a lower starting water level and more pressurized air? I think so too, but we will do the run to make sure. Simulate mode. Start the transient simulator, select the only event. Yes, as we guessed, the vessel empties only sooner. Returning to the editor. Select and edit the vessel. Setting the water level to 46.971 metres. Checking that that gives a 0.25 cubic metre air volume. Yes, it does. Simulate mode. Start the transit simulator. Select the event. Success. Viewing the route animation to get an overview of how the system responds during power failure. There is a slight positive head at the crest, node third point, and the head is slightly above the maximum allowable level at the pump delivery, closing the hydraulic grade line. Let me use the envelope report to get the exact head values at the required nodes, scrolling down to the nodes data. Here are the maximum and minimum values you need to write into the workbook. Returning to the editor. Now to analyse the case with a virtually non-existent pressure vessel containing only 0.01 cubic metres of air. Specifying the water level as 47.53, checking that the volume is 0.01 cubic metres, yes it is. Simulate mode, start the transient simulator, select the event. View the route. Without an air vessel, we see vapour head being reached over a significant portion of the pipeline, playing the animation. After power failure, things become a bit chaotic in this low friction pipeline. It's taking a long time for the water column to come to rest. I think I've seen enough. Pausing, closing the hydraulic grade line, going to the envelope report, scrolling down. Here are the maximum and minimum values you need to write into the workbook. Remember, for any system with a pressurized air vessel, the first task is to find the required air volume, or in other words, the amount of stored energy that the system needs.